Hello and welcome to the course Climate Hazards and Disaster Mitigation. Today we are going to discuss accounting non-stationarity in modeling climate hazards. What we learned last time, we appreciated climate related risks due to climate change and its role as a hazard multiplier. We learned how warming alters temperature and precipitation extremes, and we discussed the role of early warning systems and climate risk management. What are learning objectives for today? We'll understand types, will enumerate various approaches for assessing and detecting stationarity, and will discuss how non-stationarity affects climate extremes and influences water resource planning decisions. Starting with the word stationarity, the literal meaning could be something which is not moving or not changing. That is a literal meaning. But when we talk about statistics, particularly climate, this is a very important term. Now, we all know that climate varies at all scales, which will result in accelerated extremes, weather events and more violent floods and higher flood risk. If we understand the space-time variation and dependency among the variables, it will be very useful in predicting future changes, which will help us support adaptive water management decisions and disaster mitigation. Globally, there is a shift in the mean and extreme hydroclimatic conditions, which has affected the spatio-temporal distribution of floods and droughts. However, when we talk about climate change, we seldom talk about how the time invariance of the characteristics of a time series is discussed. So time invariance is a very fundamental property of a stationary time series. So time invariance means it is not changing with respect to time. So something is remaining constant. In general, stationarity means that the statistical properties of a process generating a time series do not change over time. In nature, everything will change, so we cannot expect anything to be constant. So implying the meaning that any property will not change, that would be a wrong meaning when we take into terms of stationarity. So it does not mean that the series does not change over the time, just that the way it changes does not change over the time. For example, there are two definitions provided here. If you see, the series is changing over the time, but if you take a long-term horizon and then you see, the rate of change will not be changing. That is what is meant by stationarity. But if you see a non-stationary series, so in case of a non-stationary series, you can see that, let us say you split your time series into three different parts. So here you can very clearly see it is changing, that is a rising pattern, it is showing a falling pattern, then again rising pattern. So that means the rate of change is changing over the time, and that is why this series is not a stationary one, while the series to the left is more a stationary series. So the way it changes is not changing over time is essentially what you call a stationary series, and if the rate of change is changing, then it is a non-stationary series. Stationarity refers to the property of a time series where its joint probability distribution function remains invariant to shifts in time. For a strictly stationary series, all the statistical moments of its PDF must be time invariant. So when we talk about statistical moments, the first moment is your mean, second is variance, then you have skewness, kurtosis. So these are the main moments, and so it is maintained that if all the statistical moments remain time invariant, then we can call it as a strictly stationary series. So in practical terms, a stationary process would have a constant mean, so the mean is constant, the variance is constant, and the covariance only depends on the time lag of the observations between them. So these are three essential characteristics to define a stationary process. Talking about types of stationarity, stationarity is not a one size fit all concept. It comes in different forms. So the very first one is a strict stationarity, as we discussed earlier. If all the finite dimensional distribution, that is all the statistical moments of a stochastic process, are time invariant, then we call it as a strictly stationary process. That means, let us say if you have a time series you take different segments of the time series and compute the mean. So mean is one of the statistical moment. So if mu1 equal to mu2 equal to mu3 at given value of alpha, let us say 5%, so that given significance level they remain same, we can essentially mean that the time series is stationary, otherwise the time series is non-stationary. And similarly, if we prove for all the statistical moments, we can claim it to be strictly stationary. When we talk about weak stationary, it is also called a second order stationary, in that only first two statistical moments are dependent on the time differences. You need not talk about the other moments. So if the first two moments are satisfying that criteria, then they are called weakly stationary, otherwise it is non-stationary. So the purview of weak stationary does not consider skewness and other higher moments, because they are more or less accurate to determine when short data lengths are encountered. Talking about two very well-known processes in statistics, that is white noise and random walk. So white noise is a weak stationary process. In this you can see that this is the data which we have generated, a synthetic data. So if you take mean of this data, so you can see that the mean largely remains constant and the variance is also fluctuating with respect to the mean. So in the white noise process, you get the random variable which has constant mean and a constant variance and zero mean. Similarly, you can also visualize using a PDF. So you can see that it follows a very nice Gaussian fit. But when you talk about a random, so this is a stationary behavior. When we talk about random walk, you can see that it is a non-stationary process because its variance grows with time. So if we see this particular variable, variance here, variance here, variance here, so the variance is continuously growing with respect to time, and you can see that it does not fit a normal distribution. So such processes, random walk process, is an example of a non-stationary process. What are the approaches for stationarity assessment? So you can have either a visual approach, that is called a correlogram, or statistical approach, which can include unit root test, trend analysis and change point. However, your trend and change point as well as unit root test, they are not that accurate because they do not consider all the time invariant characteristics of the time series. So at the end of the lecture, we will provide you some reference materials which will help you in getting more better approaches for stationarity assessment. Here's an example of white noise. So if we look correlogram, so for white noise at lag 0, the autocorrelation is 1. So autocorrelation is a correlation of the same data with a different time lag. So here you can see the correlation is 1 and then the correlation almost diminishes. So this is an example of a stationary process. But when we take a random walk, you can see that the correlation persists at different lags. So this becomes a non-stationary process. So rapid decay of correlogram is a sign of a stationary process and slow decay is a non-stationary process. But based on the correlogram, you cannot confirmly say it is just a visual assessment. Trend analysis, you can see that here very clearly that it is a rising trend and here the trend is almost constant. So statistically significant increasing or decreasing trend may imply non-stationarity in the time series. Predominantly, if you divide into two halves and you assess different moments, it could observe that your mu1 may not be equal to mu2, that is means are different. But always it is not the case that presence of trend will indicate that it is non-stationary. Similarly, change point. So a change point could occur if there is an abrupt shift in the time series. So here clearly you can see that your mu1 and mu2 are not equal. So this is an indication of a non-stationary process. But absence of a change point can also lead to non-stationarity. That is why The conventional trend and change point analysis methods have inherent limitations which are overcome by more advanced methods. What are the different types of non-stationary signals we can detect? So here we are representing a time series. So you can see this is a time series. The black line indicates the mean, the blue line the standard deviation. Coming to the right side of the plot, we have the kernel density plots. So they are called kernel density estimates. They are non-parametric probability distribution functions. So the red one indicates before change point and the blue one after change point. So here we have introduced an artificial change point at the mid of the time series. So you can clearly see that the mean is changing but the variance remains same, and that is what is reflected here, that after change point the mean has increased but the variance is same. So similar variance and change in mean. Next, in the second category, we see that the mean is constant between the two parts but the variance is changing, which is reflected here very clearly, where your process becomes more variable. Third, you can see that there is both shift in the mean and variance. So here the mean has also decreased while the variance has increased, which is again evident from the KDE plot. Fourth, here you can see that there are discernible trends in the time series. So the trend component is there, but if you see the KDE plot, you can see a very nice overlap between both the before and after change point. Looking at here, you can not easily tell whether the statistical properties are changing, because your mean is also location parameter and scale parameter remaining same, but you can see that the trend magnitudes are varying. So if you take the slope of these trends, they will be different. And lastly, you can see that if you take these two time series, the variance are same of these time series, the mean are changing, but there is again a trend reversal. Here it is an increasing trend, here it is a decreasing trend. So these are kind of non-stationarity signals which you will see in most time series. Let us visualize these changes. For example, I have a time series. I take different parts of the time series, so 1, 2 and 3 parts. I project this data. So when I see this data, I can very clearly see if I have this location parameters. So the location parameter is increasing. That means the time series is essentially non-stationary because it is not common. Also, if I see the variance from this point till this point for part 1, then part 2, so variance is also changing and the distribution characteristics are also changing, because you can see it is not symmetric. Here you can see it is kind of one more modality comes into picture. So you can visualize how the statistical properties are changing for a given process. Another process, we can see that in this particular time window, 1, 2 and 3, again 3 time slices. So you can see that your mean and variance both are changing when you look at this particular process. So the diurnal temperature range, if the changes are occurring, that would also cause changes in the land surface processes, and which will affect the hydrological cycle. What are the key impacts of non-stationarity in hazard? If you are ignoring non-stationarity, which will lead to under-reporting of disaster risk. Most of our hydrologic designs or flood management practices are based on stationarity. We did flood frequency analysis. So for a given return period, we are finding the magnitude. Now we are assuming that, let us say we analyze last 50 years of data, we are assuming that the rainfall characteristics or the stream flow characteristics have not changed, but in reality it is not so. Because of urbanization, global warming, the characteristics have changed and the stationarity assumptions may no longer be true. So that is why we have to assess whether the time series is essentially stationary or not. Otherwise we can lead to underestimation or overestimation of design levels and risks. Significant trend identification. Studies show that 50 to 80% of rainfall grids exhibit significant non-stationary behavior requiring dynamic modeling rather than static estimate. So most of the rainfall grids are showing non-stationarity, and you cannot rely on stationarity estimates. Increased return levels, applying non-stationary models can result in substantial increase in return levels. So if you see here from this study by Ghate and Timbadia, we have seen for rainfall the return level for stationarity and non-stationary, you can just see the difference. At lower return levels the difference is not pronounced, but as you go for higher return levels the difference is very pronounced. So if you are using a stationary curve for that is design, we derive IDF curve based on a stationary return level, it could lead to underestimation in design if scenario is actually non-stationary. So non-stationary approaches, if the data is detected, then it should be used for infrastructure design. What can be issues and implications for disaster and water management? If the non-stationarity resulting from changes in statistical properties can lead to changes in frequency and magnitude of extremes, particularly floods and droughts. It may manifest changes in the design flood magnitude which are adopted in design of dams, levees and other flood control measures. Also, if we see there are shift in the distribution and mean of temperatures, then the climate patterns as a whole can change. It can lead to shifts in precipitation, your evaporation can exceed, the intensity and duration can change, as well as the heat waves and cold waves. Non-stationarity in variance of hydrological time series can pose more challenge. For example, earlier the variance was this, now the variance is this. So it essentially indicates that the climate will be more variable. You have to account for more wider variability when you are designing. Shifts in the mean are more easy because the variance has not changed, only this value has shifted. So you can just adjust your design value theta to theta dash and you can do away with. But when you are talking about variance, so you cannot simply do theta with theta dash because the variability has increased. That gives wider uncertainty range which is to be encountered, otherwise you can face water availability challenges in future. Non-stationarity in variance can hinder detection of trends in hydrological data. It can make much more challenging to detect trends over a long period, or is it due to short-term variability. Also, it can lead to lot of uncertainties in the flood forecasting or prediction models. If non-stationarity in mean is seen, particularly in rainfall, then the stormwater networks which are designed for earlier means, they will not be sufficient and it will necessitate us to re-engineer our stormwater systems to handle more runoff. So in conclusion, presence of non-stationarity in statistical properties of hydrological systems is crucial factor that must be considered in hydrological design and water management. However, just detecting non-stationarity does not mean that it is inherent. There should be a attribution analysis. For example, we discussed correlation and causation. So there should be a causation factor which should be attributed to this non-stationarity. For example, if this is a river going on, you are measuring the flow in a river at this point of time. In future, a dam is constructed and now you measure flow Q2. If you calculate Q1 not equal to Q2 and establish there is non-stationarity, so statistically you have done, but what is the physical basis? So this dam, if it is regulating those changes, then it can be attributed as non-stationarity. Another example, same location you are measuring Q1, after certain period Q2. You find Q1 not equal to Q2, but there is no dam, there is absence of dam. Then what could be the factor? There can be precipitation. So in that case, you can check whether P1 not equal to P2, that means whether this is causing the discharge, stream flow discharge to be non-stationary, then that has to be found out. So there has to be a causative factor or an attribution. Without that, you cannot be certain about the non-stationary behavior of that process. In summary, what are the key takeaway? Time invariance is a fundamental property of a stationary time series. Hydroclimatic time series show changes in mean, variance and distribution due to climate change and human activities. Many hydrological analyses assume time invariant characteristics which may not hold true under changing climatic conditions. Shift in mean and extremes are affecting spatio-temporal distribution of floods, drought and heat waves. Non-stationarity affects design standards, extreme event prediction and necessitates adaptive and resilient planning. In a nutshell, we should include non-stationarity in our design estimate so that we enhance our capacity in disaster mitigation. Here's an activity suggestion for you. Present a comparative assessment of various non-stationarity detection approaches. For further reading, as I was discussing, we have proposed a new approach, that is non-overlapping Brock stratified random sampling approach for assessment of stationarity. You can refer this paper in ASC Journal of Hydrologic Engineering, where this approach will give you a very clear-cut distinction between two forms of stationarity, that is weak or strict, as well as non-stationarity. It dwells on multiple tests which will check the median, variance and distribution similarity, as well as the first four statistical moments and auto-correlation. An advancement of this study, that is understanding non-stationarity patterns in basin scale hydroclimatic extremes in International Journal of Climatology. This study will essentially give you what are the factors or the stochastic processes influencing non-stationarity. Whether the non-stationarity is due to changes in mean, changes in variance, changes in distribution, or a combination of that. So these two are very nice studies which will give you good guidance about stationarity detection. Thank you for your attention. The next lecture will present a course summary on climate hazards and risk assessment.